Hello everyone. I am presenting a location-independent GNSS relay attack. This work is done in collaboration between CISPA and Northeastern University. And Maryam Motallebighomi is actually the force behind doing all this work, most of it. Like these days, we cannot imagine our life without using GNSS system. For example, when I walked here in the morning from my hotel to here, I used Google Maps, and there I was using GNSS systems for positioning. And when we say GNSS, I am referring to different satellite constellations like GPS, Galileo, GLONASS, Baidu, etc. These satellite systems work by transmitting navigation messages. These navigation messages contain the location of the satellites as well as the precise time when these signals are being transmitted. These signals are transmitted using DSSS modulation at the physical layer, and the pseudo-random codes are publicly known to all users. So it is assumed that the satellites are precisely synchronized and they start transmitting the satellite signal at the same time. When these signals arrive at the receiver, they arrive obviously at different times because the signal travel with the speed of light, and the propagation delays will be different. If the satellite is closer, then the propagation delay will be smaller, and so on. At the receiver, we assume that we may not have a very accurate clock. For example, we might have a quartz clock, and in that case, we might not have an accurate reference of time. So instead of measuring the range between the satellite and the receiver estimates pseudo-ranges, and the pseudo-range from 4 or more satellite is needed in order to perform positioning as well as to correct for the clock errors. It is well known that the GNSS systems can be spoofed. Like a lot of these attacks have been shown, and many of them are being like reported in media and so on. So in order to perform these GNSS spoofing attack, what attacker can do is attacker can receive a signal at some location, at the target location, and replay it near the victim, and now victim will assume that they are at the targeted location. But in that attack, the attacker would need to be at the target location to receive these signals and then replay it near the victim. Instead, what attacker can do is attacker can generate the navigation messages, and since the data of navigation message can be generated by the attacker, and pseudo-random codes, the physical layer codes, are publicly known, an attacker can generate these navigation messages on its own. So there is nothing that is preventing attacker from doing these attacks. What has happened in the recent years is that multiple cryptographic authentication schemes have been proposed. For example, Galileo have proposed open service navigation message authentication, or OSNMA in short. And these systems uses Tesla protocol, which are one-way hash function, and they enable authentication of the messages. The keys that are used to generate a message authentication code are kept secret for a time, and they are then disclosed to the receiver after a certain time window. The receiver assume that, it is assumed that the receiver have a course time synchronization, and the receiver can validate the authenticity of these messages. And if a message arrive at the receiver after a certain delay, then this message will be discarded. So what these authentication messages schemes are doing is that they are enabling the integrity of the messages sent by these satellites. However, we all know that at the receiver, we are performing time of arrival estimation. So by using these schemes, we are preventing attacker from generating these navigation data bits, but we cannot prevent attacker from manipulating arrival time of these data bits. So we do the following. We show that there is still a possibility of performing real-time location spoofing by using software-defined radios, even when navigation messages are being authenticated. We show that we can spoof the location and the motion of the user, which is even 400 kilometers away. without manipulating the integrity of the navigation messages content and without moving to any other location. So for example, our attacker and the victim are at the same location and they are not even receiving this signal at another location. Our real-time setup have a processing delay of around 4.3 milliseconds. So any like these delayed key disclosure schemes are not able to detect that we have spoofed this signal and pass all these integrity checks. We test our attack on commercial receivers, and we also pass checks applied for by the satellite-based augmentation systems, also known as SAPs. We also evaluate the effect of different parameters on the accuracy and performance of our attack. So this is the attack overview. So like I said, like satellite start transmitting signal at certain time, and at the receiver, we are receiving these arrival time of the signals to estimate pseudo ranges. And depending on how these pseudo ranges look like, the location is estimated. What attacker here is basically doing is that it is manipulating the pseudo range estimation. So it has received the signal on the left, I think, and then no, right, on the right, and it has changes the pseudo ranges of the signal on the other side. And it's when replace the signal at the receiver, then the estimated position would be different depending on whatever delay we chooses. The location will match to whatever delays we have introduced. These are following the components of our attacker, which we have designed in our real-time setup. We have a nav message streamer, delay estimator, and spoofing signal synthesizer. So nav message streamer basically decode the data bits which are coming from the satellites. We are able to get data bit every 20 milliseconds, after that, we choose the delay estimate. Depending on whatever location we want to spoof our victim to, we design our own, like we decide on what delays we should introduce for the satellite signal coming from different satellites. And after that, we synthesize this signal so that it is acceptable at the victim receivers, like it should have a correct code phase and modulation and so on. So what our signal synthesizer do is the following. It take the target location, the location where we want our victim to. It take the satellite ephemeris data, like where these satellites are located and so on. Using this data, it calculate the pseudo ranges, like how the time of arrival of these signal arriving from different satellites should look like. Based on this information, it estimates different values needed to modulate the data so that it pertain to this targeted location, like code phase, Doppler, carrier phase, etc. It gets the data bits, the actual data bits which are being transmitted by the legitimate satellites using our nav message streamer, and they use these two information to generate the IQ samples, which are now same as like they would have been coming from the legitimate satellites. So like I talk about OSNMA, like we perform some proof of concept implementation for OSNMA, but there is not enough OSNMA signal out in the space, so we cannot test like full end-to-end system using that yet. So to check our setup, like if it works or not, we designed our live setup using TPS modules. So to do that, we have a active GNSS antenna. And this antenna is actually receiving the legitimate signal, the live legitimate signal, and then it is being fed to the USRP, and this USRP received these signals, the legitimate signal, which are arriving from the legitimate satellites, and give us the data bits that are required. Our signal synthesizer take the input from the attacker, like which target location we want to spoof, and it automatically generates the delays each satellite signal should be applied. And once our signal is synthesized, we transmit it by using another USRP, and we use a U-Blocks M89 receiver for testing whether our generating signals are being used by the receiver or not. So we evaluate our attack on both static and the dynamic scenarios. In the static scenario, we look at the offset of our attack at different locations. So for example, if we want to spoof our device to somewhere 5 kilometers away, 10 kilometers away, and so on. In order to check the stability of our attack, we run this attack continuously for each location for around 10 minutes. And we also check the integrity of our navigation data bits by cross-correlating correlation function. Basically, what we want to test is the following: whether the data bits that we are receiving in a legitimate receiver and the data bits that we are transmitting after the attack, whether these data bits are the same or not. And we also check for the integrity, whether these augmentation systems are detecting for our attack or not. In the dynamic scenario, we spoof the signal to take a shape of some trajectory that we planned ahead, and we wanted them to move with the speed of around 2 meters per second, 2 miles per second or something. And so there was this trajectory that we wanted to go around this lake and see if when our both victim and the attacker are co-located at one place, can we spoof these victim to take this trajectory. And we show that this attack is possible when victim is either stationary or victim is moving. Like it does not change the accuracy of our attack. We also analyze different parameters which can affect the accuracy of our attack. For example, sampling rate. So if we have higher sampling rate, we can have better accuracy by which we perform the attack. For example, if we have a sampling rate of 10 megahertz, then we can control our sonar ranges by like 30 meters. We also have different accuracy depending on which satellite we use for performing attacks. So if we use satellites which have better geometric resolution or precision, in that case we get better accuracy as compared to the satellite which have bad GTOP. Our attack also, like the impact of our attack also changes with the satellite, depending on the satellite orbital motion. So if the satellites, for example, in this graph, if we choose satellite offset number 1 and 4, in that case, this is a good set in a sense that we do not have to change the delay very rapidly. However, if we select set 2 and select set 3, in that case, we would have to rapidly change our delay estimator again and again. So, depending on which satellite we choose, it will affect the accuracy of the system as well as how fast we have to adjust the delay estimation. We also looked at how much coverage we can do. For example, over here, we see that at any given location, at least 6 satellites are common. So if we have at least 4 satellites common at the location we are at and the intended location, if the 4 satellites are common, then we can perform these attack right away. And around 2 observation points are enough to receive the satellite from all the available satellites. So with this attack, we provide a lazy attacker, basically, which is able to spoof any arbitrary location and trajectory without compromising the integrity of navigation message content and without physically moving from its location. We analyze the effect of different factors like sampling rate, satellite constellation, orbits, etc. And our implementation is publicly available for the community. Thank you.
Okay. Any questions? Yes. Let's wait for the mic.
Okay. So thank you very much for the talk. I have two quick questions. One question is perhaps relevant, but not directly relevant to your work, and that is, over the past couple of years, in my class when we have students to spoof GPS signals and attack their phones, the same attack works against the Samsung devices, but that same attack doesn't work against iPhone phones, and that does not have to be that wasn't the case in the prior years. Just wonder if you have any thoughts or similar observations on that. Maybe iPhone is doing something to protect against GNSS spoofing attacks.
I believe there might be two reasons that why these attack does not really apply to Apple. Maybe first is because they might have better clocks. So and the second thing is they might be saving the history of the location of the device. So if we randomly start the spoofing here that we are in Germany, then it will kind of realize that it's a spoofing signal and they just discard it.
So thanks for your insight. My second question is specific now about your work. I wonder if the receiver can check any plausibility check, whether or not those four delayed signals together make sense. So by knowing the location of the satellites on the sky, and then whether or not that amount of distances with four of them at the same time makes sense. Does the receiver do something like that?
Okay, like here, right? So
Yes.
over here, when we are introducing these delays, we are choosing these delays to match with a given location. Okay. So therefore, attacker would not be able to see it. Attacker can only detect it somehow if this delay that we have introduced, like this space where there's no arrow, if somehow attacker can detect, the receiver can detect it. But given that the reference clock at the receiver is not very accurate, it is not feasible for the receiver to detect it.
Okay, thank you.
We have one more question here.
Can you implement seamless takeover?
I think seamless takeover may work in some scenarios where there is high multipath and so on. There is a possibility it may not always work in this attack because it's like a same attack which was done earlier. There might be a possibility that we might be receiving the signal from the legitimate satellite as well as a pseudo ranges coming from attack signal. So if we can somehow still detect, it might be able to detect seamless takeover, but seamless takeover is possible to be implemented here because we can change the delays in such a way that we perform seamless takeover.
Can you talk about some of the preconditions for the work, for the attack
for
to
this
be
to
working?
work?
Yeah. For example, is there any? Do you need to know the location of the victim?
We do not need to know the location of the victim, but if we know the location of the victim, we can perform the seamless takeover attack. Because then we can inject very small energy at the location where the victim current location is, and then slowly start moving it away. And we can control our delays to a very, very precise value, so it would be possible.
And does it work for the U.S. military?
That we do not know.
In principle, there is nothing different from.
No, it's not nothing different. There is a possibility that they might be using a different pseudorandom codes. And if pseudorandom codes are not yet known, then this attack would not work because we still show that we are authenticating messages, but we are assuming that the pseudorandom codes used for modulating the data is still publicly known. So if we have to perform attack on the US military, in that case, we would need to either know the pseudorandom codes or somehow we have to use sort of directional antennas or something so that we can differentiate the signal arriving from different satellites with different pseudorandom codes.
And also when there are, for example, suppose you can do, suppose there is a GPS and Baidu and both are authenticating, then can you spoof both at the same time?
We can spoof both of them at the same time,
place?
But we would have to also design the same attack using Baidu, and then we can use it.
Okay.
Thank you.
Okay. In interest of time, let's thank Mridula again.